In the third section, we will know how to add. So somehow we learn how to multiply before we can learn how to add. And because again, this multiplication is more intuitive in terms of counting. And we have several tasks, and we have to do them all. Then we multiply them. And the question is, when do we add? And this is where we have the rule of sum. So we add things. That's only one example here. But when we add things, when the things we do are separate. So if you think about the tree diagram, right, when we have the rule of product, we have the first arrangement or the first steps. Right, then for each arrangement, we have the second arrangement, or in step 2, in the second step. So in this diagram, if you have step 1, and then each of them can be followed by by step 2. This is where we use the rule of product. But we use the rule of sum when you can kind of guess when these are actually the same step. When we have to choose to either choose the first arrangement, one of the first arrangements, or one of the second arrangements, then this is the rule of sum. And this can be summarized into just this short diagram. But in practice, you have to, be careful about describing these two steps. And here, if you can kind of like stack them together, you have to choose to either do the first one or the second one. Then you follow the rule of sum. And most of the time, but not all, there are some exceptions because of grammars and stuff. Like if you see the word or, that means you have this kind of diagram when you stack them together. But if you have the word and, or if you do something, then do something else, then these keywords almost always give you the rule of product. And for the rule of sum, there you just add them together because you stack them up. You choose from the first, one of the first options or one of the second options. So here it is. So if there are m ways to arrange something, and then there are n ways to arrange something else, this sounds like the rule of sum we have at first. But then these arrangements cannot both happen. Or in this case, you have to choose from either the first arrangement or the second arrangement. And then the number of ways to arrange either of those things is m plus n. And if you read it in this way, it might seem complicated. But we need both the idea or the concept and precise wordings of what we are doing. So you can compare them both. And this is for two arrangements. If there are two options, then here's how you add. If there are more than two options and you have to choose just one, like one of the options among those things, then we have a rule of sums where you add everything else. And this time we have to arrange either of these things. Even if there are 10 options to choose from, you have to choose just one. I don't have an image for that, but maybe imagine you need a phone. You need a single phone, or maybe that's not how you draw a phone nowadays. I don't know, maybe that's how you draw a phone. Yeah, that. Suppose you need to choose a phone. Yeah, that. A tablet. Yeah, tablet. And there is this first company, maybe some from a pear or an apple or whatever that is. Maybe the first company have three options. Maybe there are 3 different products or the same product but in 3 different colors. Maybe the second one, the SS or whatever you can name it, they give you 4 options. And maybe the last one from M, whatever they are. Maybe they give you 4 options to choose from. If you want to pick a single phone or a single tablet, then how many options do you have? Yeah, of course, it's the sum. Okay, among of these tablet products, okay, how many of them are there? 3 for the first company, 4 for the second company, 4 from the third company. That means you have 11 options to choose from. And that if you want a single phone or a single tablet, sorry, if you want just a single tablet from one of these 11 options, then there are 11 ways you can pick one tablet. So here it makes sense to just add them up, not multiply them. Because you have to choose from one of them, from either the first company or the second company or the third company. Because it's not like you choose from the first company and then you choose your second tablet from the second company and then you choose your third tablet from the third company. Now in that case, you would have to use the product. But no, just one. One tablet is enough for you to, to work on anything. And in this case, even if it sounds basic, usually we think of these things as cases. Oh yeah, I don't have it in the slide, but we think of this rule of sum as cases. If you have to do something, in this case there are several ways to perform these things, and you can separate them into cases. Maybe that's the first case, that's case 1, and then case 2, and then case 3. If there's a way to divide or to partition this into several cases, and then you compute each case separately, and at the end of the day, if you ask how many ways you can perform this task, and then you would add the first case to the second case to the third case. This is a more common interpretation, or more common way you perform the rule of sums. And in theory, you would do this in combination with the rule of product. So you first divide the task into several cases. Then usually you would use the rule of product in each case. And at the end, you add them all together using the rule of sum. In practice, this will be the way to combine these two rules. Let me give you one example of how to apply the rule of product. So in this example, suppose you want to count how many integers between 1 and 100 that are divisible by 11 or 13. It doesn't sound like rule of sum, but there's some giveaway, which is 11 and 13. You might say, okay, there's the word and, but yeah, the word and is for the word between. It's between 1 and 100. So this is giving you the range of all possible numbers. It doesn't tell you that you have to choose all the numbers. Just give you a range. And so this n is not related to the numbers we want to count. We want to count the numbers that are divisible by 11 or 13. So that's how you kind of see that you use the rule of sum. But before that, we have to make sure that these numbers are different. If you think about them as a basket, there's a basket that has a label. Okay, all these numbers are divisible by 11, and then you have another basket that says, okay, in this basket, all the numbers are divisible by 13. And the first thing is to see if the contents or the numbers in these two buckets are separate. And you need to make sure that the numbers are not in both baskets at the same time. Are they? Can you think of a number that is both divisible by 11 and 13 at the same time? Yes, there are numbers, of course, but you have to know some basic numbers, some basic facts about divisibility, which we learn in week 2 or something. So for a number to be divisible by 11 and 13 at once, then they must be divisible by the least common multiplier of these two numbers. In this case, since these two numbers are both prime numbers, we cannot divide them in any further. And so you want to find a number that has both 11 and 13 as a factor, then this can be done by just multiplying them together. So the product of these two numbers are 143. So this will be the smallest positive number, smallest positive integer that is divisible by both 11 and 13. But 143 is not in this range. And that such number exists, but it is not in the numbers that we are looking for. Yeah, so that means we don't have to worry about that number. But in probability, you have to care about that. But for now, we are limited, so this is out of range. So and actually, we have a smaller number. Like there's a number that is divisible by both 11 and 13, and that number is 0. The next number, smaller than 143, that has this property is 0. Because in fact 0 is divisible by any other integers. But again, 0 is not in this range, so we can cross them out. And say that, in this case, like for the range we have, none of the numbers can be divided by both 11 and 13 at the same time. Which means that they are separate. Thus, we can just count how many numbers are in either of these two baskets. Which we can accomplish this by using a formula, if you happen to have one formula for that. We do have a formula, but we didn't mention that. Just you can guess a formula. If you want to find how many numbers are divisible by 11, you would simply list 11, 12, and that's 11 times 2, and then 11 times 3 is 11 times 4. It's always in the form of 11 times something. Like this basket has this form. It's 44, and then 55, 66, 77, 78, 88, and sorry, I should zoom it in. So all these numbers, 66, 77, 88, and 99. How many numbers are there? There are 9 numbers. That is 9 numbers that are divisible by 11 and still between 1 and 100. Okay, so far so good. We count how many numbers are there in the first bin. And maybe I should include that formula in lecture too. I think it's free. Yeah, but anyway, if you want to count without having to list all the numbers, then yeah, you can say, okay, it is up to 100, and you want all the numbers divisible by 11. And this k, like the number k that we want, is 100 divided by 11 and then rounded down. This is a floor function. Floor function, which is to say that we round the number down to the next integer. 100 over 11 is 9.09, repeating. And if you round it down, you get 9. So that's how you get the number without counting, if you know some number fact. Okay, that's done. Right, and then for the 13, you can count if you want to. It's 13, and then it's always in the form of 13 times something. So we have 13, 26, 39, 52, 65, 78, and 91. So there are 9. I can't write. There are 7 numbers in total inside this bin. Oh yeah, let me conclude that first. And also that means if you want to get a number from this bin or that bin, you want to choose one of the numbers among these two bins. By the rule of sum, the answer is 16, because 9 from the first bin plus 7 from the second bin is 16. In terms of a diagram, you would get that for the first bin and then that for the second bin. Was 11, 22, all the way up to 99, and then 13, 26, all the way up to the last one, which is 91. So that's the rule of sum. And oh yeah, if you want to count that without listing all the numbers, then yeah, that's the same formula. So we have up to 100. We need numbers divisible by 13. So the answer is 7.6 each. There are some decimals, but yeah, if you round it down, you get 7. And so that's the rule of sum, plus some number theory facts. So if you want to choose one of these numbers, then the answer is 16. But then I should add more other examples. Maybe let me add one. Example 4. Maybe I should start from this one. So suppose you flip a coin. Suppose you flip a coin 7 times. Oh, that's number 7. If you flip a coin 7 times and count number of heads, how many results are there? So that's a simple one. We have a coin flip 7 times and count how many heads there are among those 7 flips. And the question is how many results are there. So first notice that the results here are not coins. Like we don't in this case the result doesn't care about the sequence of flips. I mean, that's one thing. You can count how many sequences of flips are there. That's one kind of question. But not in this problem, because it asks you to count how many heads. And the question is how many results, like how many results of counts are there? So if you simply ask how many heads could come up, then you can just list out the possible cases. There could be 0 heads. In this case, that means you are lucky or unlucky that your flips are tails. And this is one of the cases that gives you 0 heads. And in fact, it is the only case to give you no heads at all. So yeah, that's one of the results. What about 1? Yeah, this can come up 1. There could be 1 head. There could be 2 heads. There could be 3 heads, 4 heads, 5 heads, 6 heads, up to 7 heads. And it stops there because there could only be 8 or 9 or higher heads. And there are only 7 tries, so you can get up to 7 heads. And in these questions, if I ask you how many results are there, the answer is 8. There are only 8 results. Even though there are many different sequences of flips, if I ask you to focus on number of heads, then the answer is 8. There are only 8 heads. There are only 8 counts of heads, right from 0 to 7. So that's the answer. Which seems weird, right? Which is counterintuitive. But if you want to, for some other problems, if you want to proceed to use this in further questions, what you would do here is you would say there could be 0 head, 1 head, 2 head, 3 heads, all the way up to 7 heads. So that's why I say there are 8 results here. But each of these cases don't have the same number of cases. They are not equally likely. Like for instance, if you look at this branch and ask how many leaves are there, there's only one leaf here. The leaf where there are no heads at all has only one leaf, and that leaf is when all the flips are tails. Likewise, if you look at the bottom branch where there are 7 heads, the only leaf there is of course when you have all 7 heads. But other branches would have more than one leaves. Like the branch when you count only one head could be the leaf when the first flip is a head. That's one leaf. Or the second flip is a head. That's another leaf. And so on and so forth. You can fill up this diagram. But if I asked you to divide this into cases, and simply ask you how many counts of heads are there, the answer is 8. So that's a rule of sum in terms of if you want to divide things into cases. There are 8 cases. It's just that each case doesn't have the same number of leaves, or doesn't have the same number of results in that branch. So that's the rule of sum, in both the simplest way and not simple, and also in terms of dividing things in cases.